Welcome to video 6. Video 6 is going to delve into a little bit more of the coils and how the propagation of a magnetic field can induce a voltage in a coil that's adjacent to that particular coil. So essentially what we're doing is we're looking a little bit more at the transformer situation. Now in the past I have used the term the time constants. The time constants tau, T-A-U. When tau equals 1 we have a full cycle, if you like. That's 5 time constants. Now I have guessed incorrectly in the past the actual measurement for 5 time constants. The time constants according to most documentation actually tells us that it's 99.5. Now the number can vary a little bit depending on where you read, what you read, and what you read about it. What you're looking at here is a small application that I've built. We'll delve into some code in a little bit if you like, if you're interested. And what we're going to do is we're going to calculate time constants. The time constants come from a small calculation, the inductance L over R. Okay, L is in henries, R is in ohms, or the appropriate measurements. So if you're going to go microhenries, then use micro ohms. So what sort of really is going on here is L over R equals T. T is time constants, at least anyway, tau. And when it's 1 we have a full series. So we're going to click the calculate button. We're going to use 15 henries and we're going to use 10 ohms. Okay, so you can see our famous ramp up. Now 7.5 is where we get the complete cycle. Complete cycle sits at 99.3. Okay, remembering these numbers come from positions on the graph here, and that is a decimal. It's a decimal figure, so you've got to multiply it by 100 to get percentage. So it's 99.326 da 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 da. Okay, so that is 7.5 time constants. Or at least 7.5 seconds, I should say, which is 5 time constants. I should get it right. It is very important. Now 63.2, you can see the number here, 63.2. If we go up, we could probably say roughly about here, that is the first time constant. 86.4, so 86.4 up here somewhere. 95. I don't know, roughly about there, and then so on and so forth. So you can go through and you can take these numbers and actually calculate the line, or at least plot the points on the graph here of the time constant. Now this is the increasing time constant. So it starts from 0, okay, and then it increases. So that's 1, 2, 3, 4, 5 time constants from 0. Okay, and that gives us a figure of 99.3% of the total, I should say there, of the total time constant range. Okay, that's 99.3% of the full current that's going to flow in that coil. Okay, over here we have the opposite. So this is as a coil decays. So coil decays from tau. Tau up here is 1. Okay, we have a decaying time constant here. You can see over time that it decays off slowly. Okay, so similar sort of situation: 36.7, 13.5, 4.9, 1.8, and 0.6%. 0.6%. Where is that? It's way over here. Alright, so that's just a rough how to do it, a very rough idea. Again, I've gone through several times in a couple of different videos now. trying to explain this, and I have got the figure wrong. So 99.3 is the figure. So please, when you're listening to what I'm saying, please understand that I don't always get the figures right. This is the real figure. This is calculated. This is the calculated figure for 5 time constants. Okay, 7.5 seconds when we have an inductance of 15 henries and 10 ohms. Okay, that's what the coil is going to do. T over R equals, beg your pardon, L over R equals T. Okay. Alright, we're going to move on. We're going to show a little bit more. Okay, we're going to test these coils like that. So we're going to check from one coil to the other coil what the propagation delay is in the coil. This is going to be a very important experiment. We will go into a little bit of detail about what is going on and what's causing the fields to do what they do. Just on that, don't know if you can see that there. This is the mess that the matte glass cores sometimes make. When you're putting them together, they peel off. That's what I was talking about in the last video. Hopefully you can see that alright. Some of them are very sharp, some of them are very small, and some of them, if they do get into your skin, are very, very hard to get out. So please be careful. It's not a very nice thing to deal with. Okay, so this is it. We'll dust it off, set it up. We'll get it set up so that you can see it. For those that have said about the shaking and stuff like that, I do apologise. Videos taken and all that sort of thing are time consuming. Sometimes it does get a bit hard to sort of get these videos up, so please just be patient with me. We'll try to stop the shaking as much as we can from now on. Alright, I've got it's a basic DC transformer here at the moment. Very, very simple. A couple hundred turns on each coil. This coil is powering the little load here, very small. Sensing resistor here, scope, yellow channel, set to 1 times. On the scope itself, set to 10 times. 0.1 ohms times 10 times is 1. So that's why the scope's set on 10 times. Probe on 1 times. Okay, I got the same at the back. The bottom coil down here. The bottom coil is the input coil, and we're just sending a pulse in. 50% duty cycle, 49 Hertz at the moment. Very, very simple. It's just being pulsed by a single channel on the on my over here. So single channel on the bridge there. Just using 1 channel of it. Excuse me. Through this setup here. So it's very similar to what we had before. Okay, that's the scope. Equal and opposite, less losses. So we have a 1-to-1 turn ratio. Okay, so there's no turns difference. So the input voltage and output voltage in theory should be the same, even though it's not. We have to have a 1.1 times to get the same turn ratio, and the current you can see is a ways off. So if we RMS current 159 milliamperes, RMS current 105 milliamperes. You can see yellow channel. Okay, so 0 here, and it ducks down here. So remember the ramp up that we had before, the 97.3% or whatever it is of 5 time constants. It's sort of down here or up here on that one. So we have a little bit of flat top up here that probably doesn't need to be there. So you can see on these coils, because of the turns and because of the inductance, you can see that the on time, that the time it takes for these coils to actually get up to charge, up to the point where no more current can flow, that time is very short. and that's because we've got so many turns on the coils. So you can see that it turns here is a lot. I think from memory, I think it's about 250 turns each coil. So the top and the bottom are the same. Now, what we talked about before, again, is the propagation delay around the core. So the bottom coil down here is our input coil, and we give that input coil a big jolt of current. So we instantly switch in the voltage, and then the current rushes in as fast as it can to the coil, and that's the curve. Okay, remember it's an exponential curve, and in that exponential curve down here, that's the time it takes for the coil to actually build up, and that's changing in time. You've got to remember that build up is a change in time. So we're climbing the hill and we're doing it slowly, 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 and as we make a step, we quicken our steps up. Okay, so effectively from the bottom here, our first steps might be really, really steep, mine might be really, really hard, and as we take small steps up the hill, our steps get quicker and quicker and quicker until it flattens off, and that's why it's exponential. So the coil down the bottom is sending a current. Well, the current is climbing in the coil, but the magnetic field is moving around the core like this. Okay, both sides. The top coil sees the change in magnetic field. Okay, so the magnetic field in the bottom coil changing in time through the core is what the top coil sees. Now that when the magnetic field changes in time, you've got to remember nearly all of the magnetic field will stay in the core, that the core is sometimes, in some cases, many thousands of times easier to travel for magnetic flux than what it is to travel through the air, because again the core will have a permeability, and the permeability basically means that the permeability of the core will allow for flux very, 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 very much easier by that factor. So say for example we've got a core of say maybe 5,000 or something like that, permeability of 5,000 means it's 5,000 times easier for the flux of the bottom coil to travel through that core than what it is through the air. Okay, so air is hard for magnetic flux to travel through. A magnetic core is so much easier for the magnetic flux to travel through. Now when a core saturates, if the core were to saturate, then the magnetic flux would spill out into space, and some of the flux would be in the core and some of the flux would be outside in space. So the magnetic flux would not be able to further travel through the core. Becoming saturated means it can't hold any more magnetic flux. So again, the wave, if you like, if you want to call it a wave, I prefer to call it a wave, but the magnetic field travels as a wave and energizes this coil. Now that wave that I'm referring to is the magnetic A vector potential, and the magnetic A vector potential is a swirling magnetic field. It's got curl, so it means the curl of the magnetic field is like that, and it gives a direction and a curl around the core. So you could sort of say that it's the current, if you like, the same sort of thing as the current. So the current actually moves through the core, and you can see on our website we have a thread, you know, magnetic. Sort of goes through the magnetic field and sort of tries to describe what it will look like and stuff like that. Now the vortex in nature, all vortexes have a curl like that and a direction. So you can see that there's a spin and then there's a direction. So the direction where the vortex is traveling would be the direction through the core, and the spin around the core will be the vortex. Okay, so it's the same kind of thing. A lot of people don't believe in the magnetic A vector potential, but it is standard science, well understood, well explained. All the Richard Feynman papers talk about it. the 3 volumes of physics that he wrote about, describes it in great detail. It is a standard part of physics, standard part of science, well accepted and well known. Some people still dispute it, but I think it's just a case of just lack of understanding. Anyway, we can see on the scope here that we've got a curve. We've got a flat, and you can see that that is the current. So it's equal and opposite. So this coil up here, the secondary coil, has an equal and opposite current to the coil at the bottom. However, the top coil, and that's part of this video, the top coil has a delay. Okay, and we're going to quickly look at the delay now. Okay, so I'm going to do the best I can here. There's a big tripod that's in the way at the moment, so I'm going to have to reach over and try not to break something. Alright, the delay. Now this is going to be a little bit hard to actually show exactly because the current's very small. So what we're going to do is we're going to, actually what we might do is we might go back to 0. First of all, we'll look at that edge. Okay, so what we're looking at is we're looking at the time. We're looking at the time that it takes for the, remember the red is the input, yellow is the output. Okay, so we have a switch off here, and then you can see over here that this coil is responding to the switch off. Now you can see, if you zoom in really close, that there is a little bit of a delay. It looks like that this up here is responding before this up here. So this coil here has got a bit of a delay in here. It's sort of saying, okay, well this one here is higher and got a higher amplitude than what this one has over here at a different time. A bit hard to sort of show. Let's go back a bit. Zoom in a bit more. Too far now. We have seen the delay before, but I just want to show that there is a delay there, and it does, you can see it over time. That might be better there. Let's freeze it there for a second. So this coil here is, it's still on, okay, up to that point there, and then it drops. But whereas this coil over here is sort of going on, okay, and then it drops later. So there is a delay in time between the two coils, okay, and you can sort of see, you can sort of see it a bit better now. So the time delay, the difference in time it takes for each coil to actually respond and turn off is different. So if the coils were exactly the same, if the delay and everything was exactly the same, then we'd have exactly the same curve, exactly the same waveform on both points here, but we don't see that. We see that this coil is responding in time to the change in this coil. Remember, this is current. So anytime there's a change in current, it creates a voltage, and this coil over here is responding with a curve up here that is responding to this fall over here. So there's a change in time. It takes time for that to happen. See if we can get a better. It is a little bit sort of hard to see. It's you sort of have to. Yeah, it's a bit hard to see, but you can sort of see it. This coil is responding differently in time compared to this one. This one here is turning off. It falls all the way down to here. So there's if like it's fallen off the cliff. Okay, and that's the change in current in that one, and this coil over here is responding to that change in time. Okay, so it sort of says, right, okay, well I'm going to fall one pixel on the screen, and this one says just after that one has fallen, okay, I'm going to as well. So there's a time delay in the actual pixels on the screen and in the waveform. So this is a waveform. Remember, all these, every time you see something on the scope like this, it's a waveform. That's current as a waveform in space and in time. Okay, so there is actually you can probably see that a little bit better there now. So if we get a freeze on, we get a cursor on, we do time. We just zoom out just a tiny little bit. Okay, you can see there's a peak there. Whoop. Don't play with it too much. Okay, and down there, there's the peak there. Okay, so you can see that there is, in time, you can see that there is a difference. Okay, and here it says it's only 4 nanoseconds, 250 megahertz, and that's the peak. So it's the peak of this wave compared to the peak of this wave down here. Okay, and the slope. So if you look at the slope's very different. So remembering it's the change, so every time there's a change in magnetic field on the primary, the secondary should respond accordingly. Now obviously that's loaded, so the change in time will be slightly different. And that is the case as well. We do have the hysteresis curve, obviously, that we need to think about. So the hysteresis curve in the core is the time it takes to go through the full curve of hysteresis. So that's called the BH curve or hysteresis curve. So there is a time delay. You can see it quite clearly there. Let's zoom out and see if we can get a better read. Of course the time itself will be the same, but there you have it. So that's sort of about 5.6 nanoseconds there, but again the peaks are a bit harder to read there. There we go, back to 4.8, so it's just sort of slightly moving it. And we could do the same here as well. So if we sort of take the point where it really starts sort of tapering off, and there is sort of a difference here, but it's a different type of difference. It's about 3.2 nanoseconds, and that's the time that the primary has switched off, but the secondary, for some reason, and I can't explain this, again, there's sometimes you're looking at waveforms that you can't really explain, but it looks to me that the secondary has responded in time before the primary, which shouldn't be the case. So we've switched off up here, and the secondary has known about the switch off before it sort of happened. So a bit of a strange one. I just want to go through and focus more so now on the propagation delay in the core and what the current is doing when we sort of see the change. Okay, the change in current is what we're doing. So the up and down on the screen, the waveform, and just go back and do your study on the magnetic A vector potential. It's the change in magnetic field on the core. The magnetic A vector potential is not there unless there's a change on the core. It's a pretty amazing thing if you sort of study it in depth. You could sort of say that there is almost a tornado or a hurricane that is surrounding the core, that the primary coil is, if you like, driving or controlling or whatever, and it's, yeah, it is pretty amazing. Okay, you can see the delay just a little bit better there, hopefully. The delay in the signals, you've got to remember these are a signal. Effectively it is a signal. The change in magnetic field is a signal, a force, if you like, a driving force for the other coil. Now, to put it in science terms, the change in current is a magnetic force which generates a voltage in another coil in its proximity. Now the very same change, the very same magnetic force that is the very fundamental operation of a transformer is the same as rubbing a glass rod with cat fur. Effectively, it's a method of exciting charge or getting charge, changing the distribution of the charge in the affected area. And in this case we're talking about a coil, but if it was a cat fur and glass rod, then the cat fur would pull the electrons off the glass rod and give it a charge, either positive or negative depending on the material. And I think it's a glass rod, I think it goes negative, I think, from memory. But anyway, that's the idea. Is the change. It's the change that is the important thing. Now we consider it as a change of magnetic field, and that is correct, but you've got to remember it's the current that creates the magnetic field. So it's the change in current. The change in current, which is the magnetic force. The magnetic force, the definition, is the change in current. And again, we can see, if we go back, where's our zero? Yeah. Go back here. These curves here are the change. So that's the change. When we flat top, if there's a flat top at the top, there is no change. Okay, so the flat top itself, for example, if we were to put that right out, we slow down the frequency at the moment with 31 Hertz, and you can see there's quite a flat bit just in here, both top and bottom. So the flat bit there is no change in current. Okay, so there is no magnetic force, and therefore it cannot create a voltage. The voltage is being created over here where it's curved and where it's changed. Once we get up to a certain point, then there is no more voltage created. Okay, so what we're looking at here now is we're looking at the voltage. The bottom trace is the voltage. Okay, now if we expand it up a little bit, give that a little bit of depth. Now what I want to show, maybe if we put the cursors on, we go time. So from that point there, we can say from this point here where this cursor is here, that there's zero voltage. There is no voltage. Okay, we're going to call that point 0. Now what we're going to do is we're going to find our point on the voltage line itself, and where the voltage has changed all the way down here, okay, is, and if we call this cursor here, if we call that 97.3%, which is 5 time constants of the magnetic field, remembering in a coil there's 5 time constants to get the magnetic field up, okay, we find that the change in voltage from that cursor to this cursor is the same as the change in current up to here to get to 5 time constants. After the voltage has gotten to the 5 time constants, it flattens off. There is no more voltage to be generated. We can't generate any more voltage. Okay, it's the time rate of change of the magnetic field of the current, okay, which is the curve in here, that generates a voltage. The faster that happens, the more voltage in a shorter time will be generated. And generated always should be put in quotes, because it's never really generated at all. It's there. It's already in the material. But anyway, okay, so you can see that there is a changing voltage, and the changing voltage aligns almost perfectly with the changing current on the red one. Remember, the red one is the input coil. Okay, the input coil current is being shown in red, and the output coil voltage has been shown in yellow. So the yellow is the voltage, red is the current on the input coil. Again, the yellow is the voltage on the output coil. So from 0 all the way over to here, okay, is where voltage has been generated, and no more voltage can be generated, it goes flatline. Okay, so if we look at cursors instead of time now, if we go voltage, we're going to put that coil to, that cursor there to 0, and that cursor all the way down to there. Okay, you can see there's 500 millivolts. It's telling us there's 500 millivolts from 0 to here. Okay, and again, it's 93.7 or 97.3, whatever it is, of 5 time constants. The change in current is what generates the voltage. It's the same as rubbing cat fur on the glass rod or perspex rod or whatever. It's the same, it's the exact same deal, there's no difference. So in this setup, this is a symmetrical setup. There's symmetry. The symmetry is one coil to the other coil. Symmetry is one magnetic field ends up being equal and opposite to another magnetic field. Each magnetic field from each coil is the result of current through the coil, and the current through the coil would be equal and opposite, less losses. And that's the whole idea of a transformer. Any and every symmetrical transformer is equal and opposite, less losses, and it will never change. However, if you're to bring in asymmetry, if we were to make an asymmetrical device where we're to introduce a situation where what we've shown here is exactly the same except for having a third coil, then the third coil would have its own magnetic field. There'd be 3 magnetic fields, and then there'd be an asymmetry. So asymmetry comes from introducing another non-symmetrical. Anyway, what we're sort of trying to show here is the 2 coils can represent the partnered output coils, and what we've sort of shown so far through this video is that the change in current can be introduced anywhere. We need a change in current to get the voltage up, but the propagation around the core to the second output coil it's relative. It's a time factor that we can take into account, and it's negligible. The delay that travels around the core is very small. So that also means that there is a factor where we can actually predict to a certain degree the time it's going to take for one coil to see the change in the other coil. Now that we've measured it, we can predict it. So what we're sort of looking at is we're looking at a situation where it wouldn't be hard to, let's say, introduce another coil over here, a very small coil, I'll say maybe 10 turns of maybe 2.5 gauge wire, and those 10 turns we could pulse with a very, very short pulse, but with a reasonable with a reasonable voltage, so that we can get a reasonable current actually move through that coil, and that very fast, very sharp change in current would then potentially energize both coils. But what we'd do is we'd have a situation where both coils had to, or were forced to, work out of phase. Okay, so now we have a situation where we can bring in the asymmetry. We can make this an asymmetrical device. We could even wrap another coil on top of one of these coils,
which is very similar to how Don Smith did it. And the change in current, okay, because remember, current and the magnetic field are basically the same thing. One creates the other. You can't have one without the other. Once you have the current move very quickly around that core, okay, and again, 10 turns with say 2.5 gauge wire, then we're going to have a very fast, very sharp magnetic field that's injected into the core. And we need an input. The input has to be there. There is an element of you have to spend a little to get a little bit more back. Anyone that's in the finance game will realize that it's just a fact, and you have to do it. So in this very simple little transformer here, we have seen exactly the same process as what our partnered output coils would see. Okay, so our partnered output coils, one of the coils would conduct. Okay, so this coil over here would conduct as soon as the input comes on, as soon as the input switched on. That would conduct, and then it would fire a magnetic field back around, and then this coil would conduct. When this coil conducts, each are both equal and opposite, both carry a current, both therefore have a magnetic field, and the magnetic fields are equal and opposite. So in this machine we would have a standing wave that would be produced just over here. Okay, remembering these cores, some of these met glass cores are up to about 600,000 for permeability. So they're very, very, very permeable cores. The magnetic field is going to go through those well before spilling out to space. However, they do saturate and can saturate. Some of them are about a Tesla, so it has to be a fairly high magnetic field, but they can saturate and do saturate, so you have to be careful. Alright, so finishing this video up, video 6, we're going to keep it a little bit shorter than the others, some of the others. We've seen a principle here that is alive in every transformer. Every transformer in the world uses this, but what we need to do is we need to think about this and turn this around and say, right, this is the process that our partnered output coils are going to be exposed to, and not our input to output coils. So we're going to turn this process around. We're going to use this process, which again is equal and opposite less losses. So you've got to remember that the coils themselves will exhibit the very same fundamental facts that a transformer would, but the big difference is that we're using an input coil to get the voltage up as high as we possibly can. Once the voltage is up, then the current will follow. Okay, remember I equals V over R. So the R is the resistance of the coils, the load. The voltage, as higher we can get that up, the more current will flow. So we do have an asymmetrical device, and the asymmetrical devices need a little bit of work to get the current up, and then at that stage, the voltage up, and then at that stage, if we can find the right point in resonance, then once the resonance is achieved, then we have a machine that will produce an above unity measurement. Just want to say very quickly, if this video has helped you, please consider a donation. Helps keep our wheel spinning. It takes a lot of time to produce these videos, get these videos together. So there's a lot of effort being put in. Also our website takes a lot of effort to keep that moderated, clean, everything else. Keep the wheels spinning, keep the bills paid. So if you can afford a donation, that would be fantastic. Please consider a donation if this has helped you. Thank you.